Welcome back. Finally, we're going to talk about a little bit of close to business problems anyway. Optimization. You should have a pretty good idea why this is important. If you don't, think of optimizing profit for your business. That's the kind of thing we'll be talking about. So, with that said, let's roll. So we're going to solve real-life optimization problems. Now, this doesn't necessarily have to do with business, but it gives you an idea of how to work the business type problems. So, how do we solve those problems? One of those things we want to do is find the optimum values. That means find the minimum or maximum, and that's what we were talking about the last few times. But before, let's look at an example. Here we've got a box. The manufacturer wants to design the box so it has a square base and a surface area of 108 square inches. What dimensions will produce that box? With a maximum volume. So for whatever reason, you want to put as much as you can into a box, but also not use too much cardboard or wood or whatever it is to actually create that box. Remember, the box is open on the top, so keep that in mind. So, at the bottom here, open box with a square base. And we already said we wanted to use 108 square inches of our cardboard or whatever you're thinking about. X squared, where does that come from? Well, that is the bottom of the box. Since it's square, we'll call that length of each side x. So the area of the bottom is x squared. And we've got four sides. One side would be area, is length times width, would be xh. But there are four of those sides, so I have 4xh. And since we only want to use 108 square inches, there's our formula. The base of the box is square, the volume will be, and this is what we want to maximize, the volume will be x squared h, the bottom times the height. That's the primary equation because that's what we want to optimize. So primary, that's what we want to optimize. Next, the surface area of the box. And there's another equation. And there's our formula, the one we just saw on the last slide. Now we'd like to have just x, just one variable. So we take that secondary equation, not the one we want to optimize, the secondary equation, solve it for the variable that we don't want in our primary equation. So this is the last one. This one right here, but solved for h. There you go. Now what that means is in our v equals x squared h equation, we can take this and substitute it in where we had the h. And that's what we get. The h becomes its equivalent. Now it looks more complicated, but there's a trade-off there. The trade-off is that all we have is one variable. Everything's in terms of x. Simplify it. I would suggest you try simplifying that yourself, not only for practice, but for practice in remembering that you're going to simplify it, because notice, you know we're going to differentiate at some point. Having 27x and 1/4 x cubed is a whole lot less complicated than this, and you certainly don't want to have to use the quotient rule unless you need to. But as you can see, now we don't need to. So now we're going to find the x value that makes a maximum value of v. We're going to maximize the volume of that box using 108 square inches. And we're going to use a feasible domain. An x is negative? That doesn't make any sense. We can't have a box with a negative side on the bottom. What values make sense? Well, of course, it has to be positive, and has to be less than or equal to the square root of 108. So, using the techniques we already have, we can find that the function with v and v's equivalent gives us 6 inches for x and 3 inches for h. It might be a good practice for you to go back and work through that yourself with the techniques we've learned in this chapter so far. So here's some guidelines. You might not need these, or you might need these for a little bit until you get familiar with these problems trying to optimize. So first of all, what are the quantities we're working with? Make sure you get all the quantities. A sketch is always a good idea if possible. Write down the primary equation, and then if you have a secondary equation, solve that for the independent variables of the primary. Alias x usually, but it could be t, it could be something else. You're going to reduce it so what you're going to maximize is there, and other than the maximized variable, you only have one other variable. Very important. Then you're going to find out what the reasonable domain is for the primary equation. What kind of x's really make sense? Then you're going to find out what the maximum or minimum value is using our calculus techniques that we've developed so far. Next, example number 3. I thought it was 2. Well, it's 3. So we want a rectangular page that has 24 square inches of print. Now that means we want a border, right? We want it to look nice. So we're going to have margins at the top of 1.5 inches. Looks nice to us. But inside that border, we want 24 square inches of print because we want the words in there. We want to see what the content is. The margins on each side are 1 inch wide. Oh, this is for the top and the bottom. 1.5. Margin on the side, 1 inch wide. What dimensions do we need? Well, let's take a look at this first. Draw a picture. Well, the picture would look like this. Remember, the top and bottom had a margin of 1.5 inches. Top and bottom. On the sides, we have 1 inch margins. So if area is going to be the area to be minimized, the primary equation looks like this. Now we want to save paper, so this whole thing needs to be minimized. And that area is x plus 3 because we've got x along here. We've got a 1.5 margin here, a 1.5 margin here, total of 3. There's your x plus 3. On the other one, you've got y, but then you've got a border of 1 inch here, 1 inch here, total y plus 2. This is all a rectangle, so area equals base times height, or vice versa, it doesn't matter. So the printed area is going to be given, remember we wanted 24 inches, and that would be the x, which is right here, times the y, which is right here, the horizontal part. That's going to be 24 inches worth of print. Solving that one, because we want the original equation, the primary equation, to only have x's. So we'll solve for the other variable. There's our y equals 24 over x. And we'll substitute that back in the primary equation. This is what used to be y. So now we can multiply those. Rewrite the second factor as a single fraction. Remember, this 2 can be written as 2x over x, and that's where we get this part. And with an x in both denominators, we can add the 2 together. Take a second or two if you need to visualize that or to internalize that. So this is what it looks like when you multiply it out. So you've got 2x squared over x, 30x over x, and so on. Simplify that, and this is what you've got. But x has to be positive. We can't have a side or any part of it that has a negative value, so x has to be positive. That involves your domain. Next, we want to find the critical numbers of A. Critical numbers, that means we're going to take the derivative. In this case, since we're working with the area, we want the area as small as possible so that we can use as little paper as possible. So here's our derivative. What do you think we do next? Set it equal to 0. Our derivative is equal to 0. That'll help us find our maximum and minimum points of x. And get the x on one side by itself. Solve for x. We've got two possible numbers for x. Critical numbers in this case. However, x equals -6 doesn't make any sense. It's not in the domain, it doesn't make sense. We can't have a piece of paper that has -6 for a distance or for a length. So the only critical number is this x equals 6. That's the only one we'll consider. Using the first derivative test, that means the minimum is where we just found. X equals 6. That's where we'll find the minimum. Remember, the minimum actually refers to the area that we need. So what do we have? Since we found x equals 6, what are the dimensions? Well, our dimensions of the paper were x plus 3 and y plus 2. Put that x value as 6 in here, you get 9 inches. Y is 24 over 6 plus the 2 gives us 6 inches for the other dimension. And that's about the way it goes. It can be more complicated, but those are the basics. That's what you need to know until you actually start working some of the problems. Then you have to work with each individual problem, see what the logic is involved there, follow basically the same overall steps, and you'll get where you need to. There's some pictures, and remember, when you have the primary equation, take a secondary equation and you solve that for that variable that you don't want. So here's the one for volume, here's the one for area that we've used before, and that's it. All right, well, take care and do your best. Bye for now.